Hello everyone, my name is Jeremy Wallace. I'm a Specialist Solutions Architect here at Amazon Web Services. And I'm excited to have you join me today for our session, Getting Started with Virtual Robots with AWS Robo Maker. Today we're going to cover three main topics. First, I'll give you a technical introduction into the Robot Operating System, ROS. Next, we'll dive into how to build and manipulate 3D simulation assets using AWS Robo Maker. This will include building a simple virtual robot with the Unified Robot Description Format, URDF, and manipulating 3D gazebo world assets. Finally, we'll bring it all together and run a simple test node in AWS Robo Maker simulation. We also have a couple demos throughout the presentation. I'll walk you through the steps to create a gazebo 3D world with AWS Robo Maker WorldForge and how to include a virtual Husarian ROS bot within the 3D world that you create. Finally, I'll show you how to write and launch a simple navigation test to run in this world. Okay, so let's get started with an introduction into the robot operating system. ROS is a flexible middleware software framework for building robot applications that was designed to encourage collaborative robot application development. It contains a collection of tools, libraries, and conventions that make it easier for robotics developers to build sophisticated applications. AWS Robo Maker, which I introduce in depth later on in the presentation, uses ROS to launch applications in cloud-based simulations. So there are two main versions of ROS today, ROS 1 and ROS 2, with 6 active distributions between the two of them. Today we're going to mainly focus on ROS 1. ROS 1 Kinetic is supported with Ubuntu 16, Melodic is supported with Ubuntu 18, and Noetic with Ubuntu 20. ROS 2 has 3 active distributions, with the latest distribution being ROS 2 Foxy. So over the next few slides, we'll dive into the core ROS concepts, and then we'll end with some of the key differences between ROS 1 and ROS 2. So ROS is centered around nodes, or processes that perform computations. They can be written using client libraries in a variety of programming languages, the most common being Python and C++. Each node should implement an individual component of your robot application, but can contain more complex software stacks. The ROS computational graph is the overall peer-to-peer network of these processes or nodes. They communicate with one another over a publish-subscribe pattern with topics or a request-reply pattern by exposing services and actions for asynchronous and synchronous communication. In ROS 1, there is a central discovery server called ROS Master that provides naming and registration services to make nodes and services discoverable to one another. Nodes communicate with the ROS Master to discover other nodes and topics that are available within the distributed system. ROS nodes, along with any configuration files, launch files, datasets, 3D model assets, or really anything that makes sense to compile up with your application, are stored in what we call ROS packages. And then finally, ROS bags are a data format for saving and playing back ROS message data. You can enable a ROS bag recorder that will capture messages that are being published over your ROS topics and then store them in ROS bags for later replay. So ROS applications will commonly include many nodes and customizable parameters. So this can be complex when you want to start the whole system. So ROS Launch is a tool that makes it easy to define the complex invocation logic for your application. In ROS 1, ROS Launch files are in XML format. In ROS 2, they are in Python scripts. In order to run your ROS applications in RoboMaker, you're going to need to define a ROS Launch file for your application. So here's a very simple example that we put on the screen. First, you can see that we're setting a parameter, starting pose to a specific quaternion or an XYZ location, and then a rotation value, which is defined with roll, pitch, yaw. So we can set this to 0, 0, 0, 0, 0, 0. Next, we'll invoke a specific node, the LiDAR node, where the node type is LiDAR node run. So one key thing to know is that the node type is correlated to the executable file from your application. So those executable files are then stored within your LiDAR sensor package, ROS package. And then finally, you can include launch files to other ROS packages, or you can nest launch files within your ROS package. So in this example, we are including the spawn turtlebot launch file. And once the launch file is defined and included in your ROS package, you can then invoke it with a simple command line operation. So an example command is on the screen now. In addition, we're using RoboMaker. You can run this ROS Launch command in a cloud-based simulation. Today, many developers use catkin, which is a collection of CMake macros, to build their ROS1 applications. ROS2 uses a different build tool that is compatible with catkin and ROS1 applications that's called Colcon. RoboMaker supports ROS applications that are built with Colcon and bundled with an extension of Colcon, Colcon Bundle. Here's a quick checklist of things to look for when building ROS applications that have been previously built with catkin. First, ensure that all the dependencies that your application needs are defined within your package.xml files or within custom requirements.txt files for any Python dependencies. ROS-deps is a dependency management tool that is included with ROS and supports a wide range of libraries and commonly used ROS packages. If the package that you are requiring for your application is not available in the ROS-provided sources lists, you can create a custom sources list and include the keys for your required dependencies. Second, Colcon will build and then stage your application in an install directory. To ensure that all the assets for your application are included in this directory, double check that you have added each required folder into the install path. In this code example, we are including a launch and a worlds folder. Third, if you have any command line arguments that you use with your ROS launch commands today, define those arguments as environment variables. In the demo that we're going to do today, I'll highlight how to set up these environment variables when launching a cloud-based simulation with RoboMaker. Finally, before you get everything all bundled, run a quick test locally after running Colcon build to ensure that everything is configured correctly. You can do this by sourcing the setup.sh file in the install directory and then running any ROS launch files that you're going to want to include. So to close out on our ROS discussion, let's just talk a little bit about ROS1 and ROS2. So today we're going to use ROS1, however, many companies are starting to migrate and use ROS2. The latest release of ROS2 Foxy includes long-term support until May of 2023 and is a good choice for building new ROS applications. Highlighted here are just a few of the core changes between ROS1 and ROS2. So one thing to note is ROS2 maintains the same core concepts of ROS1 with nodes, topics, and ROS bags. However, one of the key differences is the adoption of the Data Distribution Service, DDS, a data-centric communication middleware. This distributed communication mechanism is comprised of many local data stores, removing the requirement to run that centralized registration and discovery service. For this reason, there's no ROS master defined in ROS2 applications. As mentioned in the previous slide, ROS2 leverages Python for its ROS Launch files. This enables more complex conditional logic and makes your ROS Launch process a little bit more flexible. And finally, one thing to note is many of the community-led ROS packages have either been added already or are actively being added into the community for ROS2. So it's definitely something to look at for new projects. If you want any more information on ROS2, check out the link to the blog on this slide. Okay, so now we know all about ROS. Let's talk a little bit about the simulation assets that we're going to use today. 3D simulators are popular tools for robot application developers. Here are some of the key components of a 3D simulator. First are the 3D models, or mathematical representation of an object's physical body in three-dimensional space. Next, 3D simulators commonly include a physics engine, which simulates realistic movements by calculating physical systems like rigid body dynamics. 3D rendering engines are used to build and render the graphics that show up in these environments. And finally, 3D simulators for robotics support a variety of middleware software that can be used to accelerate your robot application development. There are many 3D simulators that are available out there in the community today for robotics development. However, today we're going to discuss Gazebo, which is a commonly used simulator provided by the Open Source Robotics Foundation. Gazebo supports 3D model types in physics, multiple 3D model types in physics engines, a 3D rendering engine called Ogre, and interfaces with a few different middleware software, including the robot application system, or the robot operating system, which I have referenced throughout the presentation and will be a part of our demo today. AWS Robo Maker supports Gazebo 7 and 9, the Open Dynamics Physics Engine, Ogre, and ROS Applications. Here is a sample simulation application running in an AWS Robo Maker simulation job using Gazebo. Today, we'll talk about three main components of the Gazebo simulation. First, we'll dig into how to define a virtual robot with the unified robot description files. Next, we'll dive into 3D Gazebo worlds and discuss the simulation description format, SDF, along with common 3D mesh formats that can be used to render your realistic objects. Okay, let's start with URDF. URDF files are an XML format, and they specify the virtual 3D representation of your robots, along with all the sensor plugins. Think cameras, LiDARs, IMUs. The same format is leveraged in both ROS 1 and ROS 2. So here you'll see a simple URDF file with 2 joints and 3 links. In the next few slides, we'll dive deep into this structure and how to build your own URDF file. But first, let's start with 2 key elements of a URDF file: links and joints. A link is a rigid body with visual features, collision, and inertia properties. In the visual tag of the link element in your URDF files, you can define either a simple geometric shape, like a box, cylinder, or sphere, or use more complex 3D meshes, which can be in formats such as SDF, OBJ, or collada files. In the visual element, you can also define any materials that will add color and texture to your 3D object. The collision element is the geometry for the collision properties of your robot. By separating this element from the visuals, developers can provide simpler models to reduce the computation time when calculating physics in the simulator. The final block in the link element is inertial. This sub-element defines the mass of the object, the center of gravity or the origin, and a 3x3 rotational inertia matrix. This information is commonly provided by your 3D modeling software. In addition, you can also add contact coefficients to further tune how your object responds to physical forces such as friction and stiffness. So joints connect links together, and they can come in different types. And so one type of joint is a continuous joint, which is a hinge joint that rotates around the axis with no upper or lower limits. This type of joint would be well suited for something like a wheel. Then you have fixed joints, which is an unmovable joint, revolute joints, which is a hinge joint that rotates along the axis specified by the upper and lower limits. There's the prismatic joints, which are a sliding joint along the axis. You have planar joints, which is the motion in the plane that's perpendicular to the axis. And then finally, you have a floating joint, which will move in all 6 degrees of freedom. In this example that I highlight in this slide, you can see we have a revolute joint with 2 links to create what looks like a robotic arm. In order to interact with your robot in Gazebo, you'll need to set up some virtual actuators. To do this, you can use ROS controllers by including the Gazebo ROS control plugin. This enables you to write your ROS application code and then interact with your URDF file and those links and joints that you had defined. Transmissions will be the element, the XML element that will actually connect these virtual actuators to the joints that are defined in your URDF file. In this code snippet, what you can see is a transmission that we set up for a left front wheel. So as you can imagine, as your robot grows in complexity, you can result in very complex XML trees that define your robot through URDF. So here's a visualization to give you a sense of how large that can grow with the PR2 robot by OSRF. So to help make these more complex URDF files easier to read, modify, and extend, you can use something called a Xacro. To briefly introduce Xacros, I'll demonstrate two capabilities: setting reusable properties and defining a macro. So at its core, Xacros are XML macros that can be used to programmatically define code blocks. In this example, we're setting two Xacro properties for width and body length. We can then reference the values of these properties by using variables in XML elements. In the second example, we are setting up a macro with Xacro with a defined parameter. So in this case, we're going to create a repeated inertial to use with the links in our URDF file. However, objects might have different masses, so we want to be able to set that differently depending on which component of our URDF file that we're including this inertial in. Therefore, we can set a parameter for mass. So you'll notice that when we call the Xacro below, we set the parameter for the mass of the value of link A to be 10. Okay, so you don't need to start from scratch when it comes to building your URDF files. There's a lot of great samples out there in the community. You can find this on ros.org, and then there's a set of links on the right here that I think are helpful for getting started. So now you know all about URDF files. Let's talk a little bit more about Gazebo and some of the file structures that you'll have in your Gazebo worlds and models. What you'll see on the screen here is a sample 3D hospital world built for Gazebo with a rendered PR2 robot. This world is open source and it's in GitHub, and at the end of the presentation we'll have a link if you want to download and try it out. Gazebo uses a file format called the Simulation Description Format, or SDF, which will define things like physics, the physics properties of the world. You can define scenes that will set the overall environment, such as sky, background, and a sun. You can define lights within your Gazebo environment, which can be set to be point, directional, or spotlights. And then you can set a pose with those lights that's going to determine where that light is going to appear within your 3D world. You can also set configurations with lights for things like brightness and color. 3D models are one of the more important things within your Gazebo world, so that's going to be the chairs, walls, people, any of the objects that you have in your world. And each one of those are also going to have starting poses that define where that object is going to appear within your world. And you'll notice there's a lot of similar elements to what we just discussed in the URDF. You'll have visual, collision, and inertial XML elements that you can tweak to set up how that model is going to appear in your world. Finally, you do have some other capabilities with SDF files. You can define dynamic actors with predefined animation settings for things like walking people through that hospital. And there's much more. If you want to take a look, check out SDFormat.org and you can get a full sense for the capabilities of the SD format. Over the next 5 slides, I'm going to give you a little taste of how you'd set up an SDF file and some of the components and structure. And then in the demo, I'm going to highlight how you could take a Gazebo world created through WorldForge and then modify it and add new capabilities to it. Okay, so for the SDF format, let's start with physics. So in SDF file, you can define physics properties. So first in this list, we'll just set up gravity to Earth's comfortable 9.8 meters per second squared. And then below, you'll see the physics element where we can define some of these physics properties. In this code snippet, we have a couple elements that we've defined. One is max step size, which is simply the time step in the ODE physics engine, which we can set to 0.001 seconds. The real-time update rate is the frequency in which time steps are advanced. The default here is 1000 Hertz. So the max step size times the real-time update rate produces the upper bound of what's called the real-time factor. In this case, 0.001 seconds times 1000 Hertz would be 1, making our upper bound real-time factor 1. To give you some sense about what real-time factor will do for your applications, if it's below 1, that means your application will run slower than real-time. If it's above 1, your application is running faster than real-time. So the next thing we can set in our SDF file is the scene. So here's where we can set the color of the ambient light and background. So the values that you see here are in red, green, blue, alpha, and the numbers are represented as percentages. And this defines whether or not, and the next item there for shadows defines whether or not we're going to compute the shadows within the environment. And then we can add a setting here for clouds to appear in a sky. So this defines that scene that your Gazebo world will use. So the final area we're going to dig into here is 3D models. So here's how you can define a 3D model within a Gazebo world in an SDF file. The cleanest way is to just include a 3D model in the world instead of putting it in directly. So in this structure, what you'll notice is we have an include tag, and then it points to a model that's in a model database called bar stools. In order to get access to the bar stools model, you'll notice the export Gazebo model path above. All we'd have to do is set up all of our models in their directories and then ensure that that path is set as an environment variable, and then the URI would link up to those models that we want to store with our worlds and generate and render within our worlds. One element to take a look at here is the pose. And so this enables us to include the model, but then define a specific pose of where it's going to appear in our world. So let's say we opened up that SDF file where our model lives in that folder, in the bar stools folder. This is what it would look like. So here's where you can see what we have defined as a visual and collision elements. In the visual element, what you'll see is the mesh file, which is a collada file that we're going to include to generate that visual. And then we have a different collada file that we're going to use for the collisions. Okay, so that concludes our deep dive into ROS, URDF files, and SDF files. So now we know all the components that we would need to use in order to build a simulation, a robotics simulation in the cloud. So let's talk about how to run these simulations with RoboMaker. But before we do that, let's jump into a quick AWS Service Primer. These are some of the core services that you're going to want to know before you get started with your simulation in the cloud. So first we have AWS Identity and Access Management. This capability enables you to control and secure access to resources that you provisioned in AWS through defining permissions to users, groups, and roles. We'll highlight how IAM roles are used with AWS RoboMaker to allow your simulation to access services like Amazon S3 and Amazon CloudWatch. So Amazon Simple Storage Service, or S3, is an object storage service in AWS with industry-leading scalability, data availability, security, and performance. You can use S3 to store things like robot application logs, software bundles, and more. Finally, CloudWatch is the central location in AWS to store your logs and metrics captured from your applications, running both on physical robots as well as in simulation. So at its core, AWS Robo Maker enables customers to launch simulations for robotic applications with a simple API call. The service provides built-in support for ROS1 kinetic, ROS1 melodic, as well as ROS2 dashing, and supports Gazebo 7 and Gazebo 9 today. With a single click, you can open GUI interfaces for the Gazebo client, as well as common ROS development tools like RViz, RQT, and access to a terminal to interact with running applications. You can also run a GUI with your simulation or robot applications and stream that GUI through those applications. All the logs, including ROS bags, are automatically recorded and written to Amazon S3 for further processing and replay. In addition to the physics-based Gazebo simulation, you can also run simulations with previously recorded ROS bags. There are multiple benefits to running simulations in the cloud with AWS Robo Maker. First is access to cloud scale. The service automatically scales the amount of compute required to run your simulation, which is up to 15 virtual CPUs. In addition, you can horizontally scale by running hundreds of simulations with a single API call. RoboMaker provides enterprise-grade availability with built-in health checks to ensure simulations run smoothly and reliably. The service is fully managed, meaning that you don't need to worry about provisioning and running the Gazebo software stack, and only need to focus on preparing your ROS application. RoboMaker is integrated with multiple AWS services, enabling you to easily extend cloud functionality like CloudWatch logs, ML services, data storage and analytics services, and more to your simulations. Finally, with pay-as-you-go pricing, you only pay by the minute for the resources you consume. One simulation unit or one virtual CPU and 2 gigabytes of memory only costs about 0.67 cents per minute. Okay, so for our first demo, I'll run a virtual Husarian ROS bot in a 3D world using AWS RoboMaker WorldForge. The Husarian ROS bot is a great educational platform for learning how to build ROS applications. For more detailed information on how to get started with Husarian and RoboMaker, you can check out the link below to our AWS Robotics blog. All right, let's get started. So first, I'll click into the RoboMaker console and open Simulation WorldForge. The first step is to create a new world template. When building 3D worlds with AWS RoboMaker WorldForge, you first need to define a high-level floor plan. Here, you'll define the number and type of rooms you'd like to include in your world and how they'll connect with one another. WorldForge automatically assigns flooring, wall materials, and furniture based on the room type. However, you can customize this. Remember, when spawning your robots in a WorldForge world, to use a center coordinate 0, 0, 0. This is to ensure it doesn't conflict with any piece of furniture. Okay, so now let's build this. So first we will start with a pre-built template. So with RoboMaker WorldForge, you have 4 pre-built templates to choose from. Today we're going to use the 1-bedroom apartment. The first thing I like to do is set a name for my template. Since I live in New York, we can set this to my NYC apartment. You will notice 4 rooms are defined: a bedroom, living room, bathroom, and kitchen, much like my apartment. For any of these rooms, feel free to customize the type of furniture, walls, or flooring, as well as the size of the room. Since we are in New York, I'm going to change some of the sizing here. Okay, now let's generate the worlds. So first, we should have some variability in our worlds, so we'll add 2 floor plans with 2 variations. Awesome. Okay, so now let's take a look at these worlds. Yeah, that is about the size of my apartment. To prepare my application, I'll use a development environment in the cloud. First, we'll clone the Husarian ROSbot code. But before we go further, let's take a quick look at the Husarian ROSbot URDF file. You'll notice a file, rosbot.xacro. This is the macro-enabled XML file that will generate your virtual robot. Here you can see we are including some other Xacro files, in addition to specifying the various links and joints. If we scroll down to the continuous wheel joints, you can see the joints are connected to a simple transmission, much like we described in the earlier slides. So to get started with WorldForge, I'll make a small modification to one of the launch files to launch a WorldForge world. Then we'll run the dependency installations and the build and bundle commands to prepare our application for RoboMaker. is the build tool that is required to use RoboMaker, and it is compatible with catkin applications that use ROS steps for all the required dependencies, which is why I didn't need to modify anything in this Xacros app. Once ready, I'll create an S3 bucket to store my bundle and then upload the bundle. After this is done, we can go ahead and launch our simulation. So first, we'll press Create Simulation Job. Here we can set the desired duration of the job, the failure behavior. If we set Continue for the failure behavior, the job will continue to run despite an application level failure. This is good for debugging. We're using ROS Melodic today, and I've pre-provisioned an IAM role to give the simulation job access to the bucket that stores our code. You can choose to set a ceiling for the amount of the simulation units. Today, we'll keep that at the default of 15. The output destination will define where your logs and ROS bags are stored. For networking, here's where you can define a virtual network and subnet to run your simulation job. For today, we'll just leave this as the default. And then finally, if we want to tag our jobs, we can do that to easily find them in the future. So in this example, we only have a simulation application. So we'll select None for the robot application. In the simulation application, as we progress, we'll create a new application that will enable us to run SLAM to build a map. This is a ROS package that's provided in the Xacros ROSbot description. So first, we'll name it and select ROS Melodic as a software suite. Next, we'll set the launch package name to ROSbot description, and then we'll also set the launch file to the gmapping launch file. Finally, we'll click Run with Streaming Session. This will enable us to attach a GUI to the simulation application itself. So in the bottom section, this is where we can define the WorldForge world that we created. So here we'll select one of the worlds and then press Next and confirm. And then once that world is selected, we'll at the bottom click Next and then confirm all of our inputs. And then finally, we can launch our simulation. This will normally take a minute or two. All right, so now that our simulation is running, we can connect to Gazebo. Here, you'll see a world that we created. Next, we can open up the simulation application as well as a terminal. In the terminal, we will start a teleop package to move the robot. As you can see, we are using SLAM packages to build a map. In the last part of this demo, let's export the WorldForge world we created and inspect the package and make a change to the SDF file. First, we'll select our world and then press Create Export Job. Once the export job is complete, we can download the package from S3 into our Cloud9 development environment, unzip it into our workspace source directory. In here, you'll see a main folder, AWS RoboMaker WorldForge packages. In here, there are two folders. One is a ROS package with any generic shared models, such as furniture. The second package has your generated SDF world file with the walls and flooring models. Let's modify the world and add a scene with some clouds. Next, we'll run another build and bundle command, then copy the bundle to S3, overwriting our old bundle. Now we can simply go back into RoboMaker and clone the previous simulation job. Once the simulation job is running, you can see our new world, now with clouds. Okay, that's all I have for this demo. Let's talk about some common use case patterns for RoboMaker in simulation workflows. So an important part of the software release cycle is ensuring that code changes don't have unexpected consequences on robot behaviors. One common use case, once your 3D model assets and simulation application has been created, is to run automated regression testing using RoboMaker simulation. AWS RoboMaker enables you to flexibly run these regression tests in simulation with custom parameters through the API. This makes it easy to connect existing CICD tools such as Jenkins, Travis CI, Circle CI, and AWS Code Pipeline to RoboMaker to run these tests automatically. So you might be wondering, what are the types of tests that folks could run in a simulation? So here's a couple examples. For a low fidelity simulation, that can be leveraged when testing things like the communication pipeline, external fleet management software, and when you're running software load tests. When scenarios start to require physics engines to test the real world conditions, that's where 3D simulators like Gazebo are a good option. Today, running Gazebo-based simulation in RoboMaker is particularly well suited for medium fidelity simulations to test things like localization, planning, and behavior algorithms. Finally, high fidelity simulations are required when your test scenarios include things like vibration behavior, slippage, motor saturation, or perhaps you have some high accuracy perceptions that you're going to want to perform within your simulation. Robot application development and testing will likely include using multiple simulation tools for different types of scenarios. So today what we're going to do is build a simple navigation test that we can run automatically within a CI pipeline. With AWS Robo Maker, you can use a ROS Launch file with defined environment variables to run test scenarios. In this example, we're defining 2 parameters and setting the value to an optional environment variable with a default value. This way, we can override the default variables through the AWS Robo Maker API. Okay, so once your simulation job is running, so once we have our test running, we're going to need a way to report the results as well as stop the test once it's completed. So AWS RoboMaker provides 2 local services in your simulation job to enable this workflow. First, you can use the add tags service to report the results of the test as a tag to the simulation job. This enables your downstream processing applications to get access to the test results with a simple describe sim job API call. Secondly, once a test is complete, you can stop the simulation job before the defined timeout to optimize your costs by using the cancel job service. Here are 2 of the code snippets that enable you to implement this logic in your ROS-based applications. Also at the bottom there is a link to a sample application that includes this code as well as a sample test node. In the final demo, I'm going to include a Husarian ROSbot description ROS package in the provided CloudWatch sample application from RoboMaker in our GitHub repository. To download the sample application, check out the GitHub link below. To do this, I simply added a line in the .ros install file to clone the GitHub repository for Husarian as part of the ROS workspace update command. Next, I'll run the ROS workspace update to then clone this additional repository. After it is cloned, I'll make a couple small changes. If you're interested, the test logic is stored in the test nodes package in this sample application. Take a look at the code in the navigation test Python script. Here you'll find the same code snippets that we described in the earlier slide. The first change that we'll make is to create a new launch file for the Husarian ROSbot. Let's open CloudWatch Simulation, then copy the WorldForge Turtlebot navigation file and rename it WorldForge Husarian Navigation. Then we can swap out Turtlebot bringup launch files with the ROSbot bringup launch files. After we are done, we can save this file. The next file we'll copy is the test world launch and rename it to test world Husarian launch. Here, we'll reference the new WorldForge Husarian navigation launch file that we just created. Our final step before we can launch this application is to generate a map for our WorldForge world. A handy script is provided in the CloudWatch sample application to do this. So the first thing I'll do is run this script by just defining the WorldForge ID that we've built and included with this package. It will store the generated map in the CloudWatch Simulation Maps folder. This 2D map is used for navigation in this demo. Okay, there it is. So once this is done, we just need to ensure the Husarian ROSbot is referencing the map. For today, I'm going to modify the argument in the ROSBot navigation package. Okay, so now that we're done everything, let's go ahead and launch this sample application. So we'll follow the same process as the previous demo, this time including the robot application that was provided in the CloudWatch sample. In the CloudWatch sample application, the robot application just simply sends metrics and log data into CloudWatch based off of the operation of the robot. For the simulation application, we'll also add an additional environment variable, navigation success count, to set our test to successfully complete itself once a single navigation goal is reached. You can change this value to any number of success counts to test a number of navigation goals as part of your workflow. Okay, let's go ahead and launch this simulation. And then a few minutes later, here it is, our test is running. Once complete, the simulation will self-terminate. Let's go check the tags and see if we have successfully passed our navigation test. All right, looks like everything's good. And that's all we have for this demo. In addition to the simulation service, the RoboMaker team has created and published multiple useful assets in our open source GitHub repository. This includes cloud extensions that can be included in your apps to easily upload things like ROS bags to S3. You can connect to AWS ML services for things like text-to-speech, natural language comprehension, image recognition. You can upload logs and metrics to CloudWatch, or even stream live video through Amazon Kinesis. We have provided also multiple 3D worlds for Gazebo that you can use out of the box to accelerate some of your simulation workloads. So here's the link to our GitHub repository where you can download these assets. Okay, so that's a wrap for today's session. But before I go, I'm going to leave you with this list of resources that you can use to get started. So thanks so much for joining, and we'll talk soon.